Hello class and welcome. Today we're going to be talking about the work done by non-conservative forces. Work done by non-conservative forces. Okay? So remember last class, our last lesson, we talked about there being two really different types of forces. You have conservative forces, and these are forces where the work done is going to be transformed and stored as potential energy. So the work done here can store potential energy. And we talked about non-conservative forces. So a non-conservative force, well, the work done by this force is going to be turned into sound or heat or something like that. So we say the work is not stored. All right, what are some basic examples here? Well, a conservative force is going to be something like gravity or something like a spring. Something where the force done by this object here is going to actually store energy. Non-conservative force, well, what's that? A really good example is going to be friction. When you have work done by friction, that energy is not stored. It's actually transformed into heat or sound energy. Another good example is drag. All right, so again, the work done by drag is going to be transformed into some sort of waste energy that you really can't use anymore. And here's something you might not have thought about. A non-conservative force could also be an outside push or pull. Because remember, a non-conservative force can have positive work, and work can be added to the system. So energy can actually be added to the system from the outside. Okay? That would still be considered a non-conservative form of work. Okay, so we're going to talk about the overall theory here. And then we're going to run through a couple examples. The basic skill you're going to be learning today is, of course, how to calculate and use the work done by a non-conservative force. So, what's the theory? Well, let's start out with the basics. Let's say this box represents my kinetic energy. It's my motion energy. And let's say I want to change this energy. Well, in order to change it, by physical law, I must do work on it. I can do negative work and remove kinetic energy from the system, or I can do positive work and add kinetic energy to the system. So I want you guys to think of work, the total work on a system, as your change of kinetic energy. In fact, your total work is defined as the change of kinetic energy. Okay? Now, let's make it a little bit more complicated. Your total work is comprised of all the conservative work that's done on the system and all the non-conservative work that's done on the system. So really, if this is your kinetic energy, there are two ways to add or remove energy. We represent conservative work with the lowercase c in the subscript, and we'll represent non-conservative work with an NC for non-conservative. Very creative. So as an equation, what does it look like? Well, your total work is equal to your conservative work plus whatever your non-conservative work is. And remember, all three of these values can be either positive or negative, whether or not we're adding energy to kinetic energy or removing it. Okay? Are we making it go faster or are we slowing it down? Well, let's think about what happens to these two forms of energy. Remember, by definition, the work done by a conservative force is going to be stored, okay, as potential energy. So basically what's happening here, I'll draw another little box. You have kinetic energy here. All right, here's your conservative work. So if you're using conservative work to take energy away from kinetic energy, that energy is going to be, by definition, turned into potential energy. See, okay, I need to change this to a U because in class we use U for potential energy. And in fact, I should really change this to a K also, just so we're consistent here. So look, if we're taking kinetic energy away with a conservative force, it's getting stored as potential energy. And if we're adding kinetic energy with a conservative force, well, by definition, it's coming from potential energy. So there's kind of trade back and forth between the two, okay? That's monitored by the conservative work that's done. But we still have this non-conservative work down here. That's taking energy either out of the system entirely or adding it into the system from outside completely, okay? Now, how do we represent this mess as an equation? Well, it's going to work a lot like this. So your change in kinetic energy is equal to your conservative work plus your non-conservative work. Another way to write this is this. Your change in kinetic energy is equal to, well, as it turns out, your conservative work is equal to the negative change of potential energy. Let's see why that might be. If I were to add 5 joules of energy to kinetic energy using a conservative work, that would be a positive value of conservative work, but that would mean I'm taking 5 joules away from my potential energy. So it's kind of like I'm going to the energy bank and I'm making a withdrawal of 5 joules, and that's going automatically into my kinetic energy, okay? So if this is positive, my change of potential energy must be the opposite. Make sense? So I'm just going to rewrite here negative change of potential energy plus my non-conservative work. All right, so let me draw this diagram one more time. In fact, I'm going to knock out conservative work altogether. And we're just going to say that somehow kinetic and potential energy can interchange and transform from one to another. And I'm going to put a nice big box around this both. And this box is going to represent what? My total energy. Because remember, class, kinetic energy plus potential energy is equal to your total mechanical energy. This is all your kinetic and potential energy added together. Now, up until now, we made the assumption, or in the previous videos, we made the assumption that this is going to be constant. That's the law of conservation of energy. But remember, there is a caveat. We said if no energy is added to or removed from the system. Well, what if there is energy added to or removed from the system? The way that's done is through non-conservative work. This is going to be work done by some sort of outside force, or work done by friction, or some way to either add or remove energy from the system totally. Okay? So I'm going to rearrange this equation a little bit. I'm going to bring this down here. And let's see what you think of this. Your non-conservative work done on a system is equal to the change of kinetic energy plus the change of potential energy. Okay? See how I took this delta U right here and I just added it to both sides? And then I flipped both sides of the equation. And we're going to end up with this. And this is just a statement of what we said exactly over here, okay? Look, your total kinetic energy, your total potential energy, this is your total mechanical energy put together. The only way for this to decrease or increase is through non-conservative work. So we can write this. Your non-conservative work is equal to your total change of energy. Or I should say, your change in total mechanical energy. All right, so basically this is the theory of a non-conservative work. So I'm going to take this result and combine it with 2 other results. And if you need to see those diagrams again, you can just go go backwards in the video. Okay. First, the result is going to be this. This is the work energy theorem. This says that the total work done by a system is equal to the change of kinetic energy. Okay? The second result is this. Your conservative work is equal to your negative change of potential energy. So if conservative work is positive, that means you're withdrawing energy from your stored energy account. Okay? If your conservative work is negative, that means you're going to be adding energy to your stored energy account. And finally, your non-conservative work is equal to your total change in mechanical energy. These three ideas together, they seem very simple. And actually, it took physicists a very long time to figure out energy just because it's a little bit abstract. In fact, we didn't really understand energy until about 200 years ago. And when you consider that Isaac Newton was in the 1600s, it's a very recent development in physics. Okay, so I just want to kind of hit the point here. So this is a very powerful idea in physics. The idea that you can keep track of non-conservative work, your total change of energy, your total change of kinetic energy, your stored energy, all this stuff, it applies to an incredible diversity of problems. Everything from atomic physics to ordinary mechanics where you're tossing a ball up in the air. Okay? This is an extremely powerful idea in physics. All right. So let's go ahead and do an example. Let's see, I do think I need more space here. Okay, so in this example, we're going to be looking at a simple physical problem. We're going to be comparing our initial and final energies. Okay, what do I mean by energies? I mean kinetic energy, potential energy, and total energy for the initial and final states of this problem. We're going to be doing this in this problem to find the non-conservative work done on a guy who has a parachute. Oops, excuse me. Done on a parachutist. Okay, so this parachutist has a bridge that he's jumping off of. But he's going to be okay because he's got a parachute, by definition. Alright, so there's this super tall bridge. It's going over some sort of gorge or something. And there's your little guy. Again with a broken spine. And this guy weighs 150 kilograms. Excuse me. His mass is 150 kilograms. All right. And he's going to be jumping from rest. I'm not sure how you exactly jump from rest, but it means his initial velocity is going to be 0. And then he's going to fall all the way down to the ground, way below. There's his parachute has been deployed. All right, so he is touching the ground. He's actually impacting the ground at a speed of 4 meters per second. This is his impact speed. All right, and he's still 150 kilograms, and this bridge is going to be really high. In fact, let's go ahead and make it 300 meters tall. So the bridge is 300 meters above the bottom of this canyon or gorge, or whatever you want to call it. Okay, and in fact, let's go ahead and set the bottom of the gorge here. Let's say this is my h is equal to 0 point. And up here, of course, h will be equal to positive 300 meters. All right, so our job here is to find the non-conservative work done on the system, okay? And of course, what sort of non-conservative work are we doing here? Well, the parachute is creating a lot of drag, so the drag force of the parachute is going to be doing work on the system. So this non-conservative work is going to be done by drag. Now I want you guys to pause and think here for a second. The non-conservative work, the number we're about to find, is this going to be a positive number or a negative number? All right? So I want you to think about this. Will your non-conservative work be a positive number, or will it be some sort of negative number? Okay, and why? We'll come back to this later. I want you to think about this for now. Now we're about to solve this entire problem, and I want to tell you this. We are not going to need. We're not going to need the standard stuff you need for a problem like this. We don't need the total time of flight. We don't need to know how long it took him to go down. Okay? We don't need to know even, where he hit his parachute. So we don't need to know the details of his flight beyond what we already have been told. We know his final velocity, we know his initial velocity, and we know his mass, and we know how far he's fallen. And let's go ahead and say that the moment he steps off the bridge, that's the initial state, and the moment when his foot first hits the ground, that's going to be the final state. So initial and final. We don't have to worry about these times. It could take him an hour to fall down. I mean, probably not. But it doesn't really matter how much time it takes. And that's kind of typical of energy problems. You don't really need to know anything about time. What are the steps to solve this problem? Well, first, we are going to find our initial kinetic energy, potential energy, and total energy. Then, we're going to go ahead and find our final kinetic energy, potential energy, and total energy. And then we're going to find our non-conservative work, by using this equation. All right, and for the initials, we're going to use the subscripts I. Those are my initials. And for the final energies, we're going to use the subscript F. Okay, just so you know what's going on. All right, so let's go ahead and get started. Okay, what's my initial kinetic energy? Well, you know what? It's just 0. It's 0 joules. I'm going to scroll back up here. Remember I said he's jumping from rest. That means his initial velocity is 0, and his initial kinetic energy is equal to 0. Okay? He has no motion energy when he first jumps. That's not a very good U. So getting used to this this tablet I'm using. Okay. So what's his initial potential energy here? Well, I'm going to cheat. I've already calculated it. It's 441,000 joules. How did I get that? Remember, potential energy is mgh. So it's mass times little g times his height. Mass, little g, and his height is 300 meters. And to get my total energy, guess what? I'm just going to add these. Ooh, that's not a plus sign. What are you doing? All right, I'm just going to add these both together. So my total energy in the initial is going to be 441,000 joules. That is a lot of initial mechanical energy. In fact, if this was a type of problem where your total energy was conserved and no energy was lost or gained, then this would also be your final total energy, right? So if you think about it, he would be hitting the ground with the final kinetic energy of 441,000 joules. Okay? I'm going to do the math for you right now just because I'm interested. It turns out this is going to be 76.7 meters per second. This is if the energy was conserved, right? So this is not good. You cannot survive an impact with the ground or even with water at 76.7 meters per second. That's something like 160 miles per hour. So that's not going to be survivable. Guys, think about it. What's the point of a parachute? Your parachute's job is to take energy away from your system as you fall. Okay? Why is it hitting the ground at 4 meters per second? Because the parachute has absorbed, well, really the air has absorbed all the extra energy. So it's not always a bad thing to have drag and friction. Okay. Now, let's go ahead and find my final kinetic energy. Again, I've cheated. I've already done the calculation. It's 1,200 joules. How did I get that? Well, kinetic energy is 1/2 mass times velocity squared. So it's going to be 1/2 times this mass, 150, times this velocity squared, 4 meters per second squared. And this is v squared. Okay, guys, be very, very careful about this squared here. It's very easy, and in fact, I saw that in the last quiz. It's very easy to forget this squared. So just don't forget that, okay? Now that's going to be a whole heck of a lot lower than 441,000 joules. In fact, if you think about it, this is the energy that your legs have to absorb when you land a parachute. So your legs are your natural shock absorbers. They're going to absorb that energy of the impact. And you can totally absorb 1,200 joules without breaking any bones or anything. Okay? This is actually totally survivable. Okay, now, what is your final potential energy? Guys, it is 0 joules. All right? So how is it 0 joules? It's because mgh, your mass times 9.8 times your height, which is 0 meters. Now, I want to point something out. So let's go back up here for a second. I knew the bridge was 300 meters off the bottom of the canyon, right? And I set my height is equal to 0 point at this point. Would it have made a difference if I put height is equal to 0 up here, and I made this height is equal to negative 300? Would that have made a difference? Well, it would have changed my potential energy, initial and final, but I think my change of potential energy would be the same. So you are free to choose what's called a reference height. That's where height is equal to 0. And as long as you're consistent, just like picking an origin, as long as you're consistent, your problem should come out okay. All right, now I am going to need a new sheet here. All right. So the last step is, well, what's your change in total energy? Remember, the change of any variable in math or science is going to be your final minus your initial. All right? So your final energy, your final total energy was 1,200 joules. And your final initial energy, your initial total energy was 441,000. Okay? So it's pretty easy to see. Your change of energy is going to be negative 439,800 joules. Okay? And remember, from our definition, our non-conservative work is equal to your change of energy, which is equal in this case to negative 439,800 joules. So we solved the problem. Now let's think about this. Negative this amount of energy means that this much negative work is done by drag. Okay? So your non-conservative work is negative, and it really has to be negative Because the parachute is removing energy from your system. Your parachute is trying to slow you down as you fall. So it's got to be negative because energy, your total and mechanical energy, is going to be removed and changed into other forms. Noise, heat, eddy currents in the air, things like that. All right, and I want to make another point. Again, the energy part of this problem is pretty simple, pretty straightforward. It's literally just addition and subtraction. It's the setting it up that can get you into trouble. Okay, so let's go ahead and do another quick example. All right, so if you're a driver, then you know about these things called on-ramps. And somebody thought, can have that. Okay, so somebody thought it was a good idea so that every time you get on a highway, you are not only having to speed up from surface street speeds to highway speeds, but you're also having to do it uphill. So highway engineers have to be very, very careful about how they design their on-ramps. If they're too steep or they end up going too high, your typical car is not going to be able to speed up fast enough to reach interstate speeds. These are the worst cars. What am I doing? I've seen cars all my life. I think I'll be able to draw one. Okay, there we go. All right, that is barely passable. All right. So in this on-ramp problem, okay, what's going to happen is I'm going to tell you a couple things. So first of all, the mass of this car is 1 metric ton. All right. And the speed you start off at, let's go and make this a little more realistic. All right, so this goes to the highway. So the speed you start off at is going to be a nice slow 10 meters per second. And the speed you have to end up at is going to be 30 meters per second. Already you know that energy has to be added to the system from the outside, okay? This car, as it's going uphill, it is gaining potential energy. Right? It's getting higher, so it's gaining potential energy. So how is it speeding up? The energy has to come from something else. So what's happening here is we have non-conservative work being done on this car. Let's go ahead and make a couple of height markers here. So this is where the car starts off. This is your initial height or initial condition. This is going to be your final condition. Okay, so here's what we know. First of all, your drag and your friction together are going to do work on your car. We'll call this NC1. So the non-conservative work done by drag and friction and all that stuff is going to be negative, of course. It's going to be negative 130,000 joules. And there's another source of non-conservative work. So this is actually trying to slow your car down, but the other one is trying to help you out. It's trying to speed your car up. It's the work done by your engine. Why is this not considered part of the total mechanical energy? The engine is a mechanical part, right? Well, mechanical energy is defined as your motion energy plus your energy stored in purely mechanical forms. So that means springs or gravity. Think about like 1800s technology, even before that. So you don't have the steam engine, you don't have the automobile engine, you don't have electrical motors or anything like that. So the engine is actually adding energy. It's taking energy from your gasoline, turning it into thermal energy, then turning it into motion energy. So it's non-conservative work. In this case, it's actually a positive. It's adding it's adding energy to your system. It's going to add a lot. It's going to add 630,000 joules. Okay? So, you're given all this information, and the crazy thing is, we're actually going to be finding height. So, you're being asked to find the height. Okay, so can we do this? Yes, we can do this with energy. In fact, we can solve it without knowing the shape of the ramp. We don't need to know the length of the ramp or the angle. We don't need to know how much time is given for the car to go from the initial point to the final point. We don't need to know any of the other information. All we need to know is how much work is being done by drag and friction, how much work is being done by the engine, and what are your initial and final speeds. So what's our strategy going to be here? Well, it's going to be a little different from last time. We are going to still find the initial energies. So the initial kinetic, potential, and total energy. But our second step is a little bit different. We're going to be using the WNC is equal to your delta E equation. All right, to find the change of total energy. And then we're going to evaluate our final kinetic energy, potential energy, and total energy. All right? And finally, we're going to use your potential energy is equal to mgh to solve for h. So that's where the h is going to come from finally. That's the strategy here. Now the first step is going to be just like the first step in the parachute problem. Well, what's my kinetic energy? That's going to be 50,000 joules. Mr. Entwistle, how'd you get that? Well, watch. It's 1/2 m v squared. Okay? This is your mass, and this is your velocity squared. This is your initial velocity, okay? And this is your initial kinetic energy. So 10 squared is 100. We get 100,000, and then we divide it by 2, we get 50,000. Now, what is your initial potential energy? Well, again, we're trying to find the height of the on-ramp, but we don't really have a coordinate system set up yet. So I'm going to say that where the car starts is going to be its reference level. So that's where h is equal to 0. And then up here, well, h is equal to h. All right, I'm sure I'm breaking some sort of math rule there, but whatever. All right, so your initial potential energy, the way we've defined it, is going to be 0 joules. Now, what's your initial total energy going to be? Well, I think it's pretty self-evident. Okay, so our next step is going to be this. We're going to use the WNC is equal to delta E equation. Okay, so we know our change of energy, our change of total mechanical energy is going to be WNC, but you know what? We have two sources of non-conservative energy. We have the drag and friction, which is going to be a negative contribution, and we have the engine's force, or the engine's work, which is going to be a positive contribution. Okay? So WNC1 plus WNC2. So this is going to be negative 130,000 joules plus 630,000 joules. When we combine these two together, we're going to get 500,000 joules. So even though your drag is slowing you down, your engine is helping to push you along. It's doing more work than your drag, okay? So that means we can increase the total energy. By the way, if you're driving along highway speeds and you're going the same speed on a level road, then the work done by your drag is equal and opposite to the work done by your engine. Okay? So your engine's pouring energy into the system and drag's leaking energy out of it. And if these two match up, well, your total kinetic energy is going to stay the same. But we're not going to worry about that right now. All right. So my total change of energy is going to be positive 500,000 joules, right? Okay. So now we need to evaluate your final energies. So your final kinetic energy, your final potential energy, and your final total energy. So what's your final kinetic energy? Well, you can find that out directly. It's going to be 450,000 joules. Okay, how did I get that? I cheated, I did it ahead of time. It's going to be 1/2 times 1,000 times 30 squared. Mass times V squared. Now, what's your final potential energy? Guys, we don't know yet. We know it's mgh, but for now, this is going to be an unknown. And you might think you'd add these two together to get your final total energy, but because this is an unknown, we can't. We can't add 450,000 to something that's unknown. We're going to do it a little indirectly. Watch this. Your final total energy is going to be equal to 550,000 joules. And I bet you can already guess how that happened. Well, your initial total energy was 50,000 joules. And your change was 500,000 joules. Okay? So your final total energy is 550,000 joules. This is what you start off with, and this is what the total non-conservative work has added. Okay? I think you guys can probably tell me what to do now. So we just have to solve for h. We know m, we know 9.8 is g, and we're going to solve for h here. Just for interest, I'm going to actually solve for my final potential energy first, just so I can keep track of what's going on. That has to be 100,000 joules. Okay? And then I know my final potential energy is equal to mgh. So I know mgh is equal to 100,000 joules. All right? And I end up with h is equal to 10.2 meters. That's the height of my ramp, about 30 feet. And for those of you who like to see what's going on under the hood, so to speak, that's 100,000 divided by mg. By the way, I'm using 9.8 instead of 9.81 in this unit. It just makes these numbers a little bit easier to work with, and we're really close to the true value. And by the way, G does vary from place to place on Earth, so I think I'm totally justified in doing that. Okay, so again, we're done. The point I want to make is that the energy part of this problem is fundamentally addition and subtraction. It's simple once you get the hang of it. And that's why physicists like energy so much. Even though it's abstract, how do you point to something and say, oh, that's kinetic energy, or that's stored energy, or this is your total energy of the system? Even though it's abstract, it really does simplify basically any sort of mechanical physics problem you can think of. Okay? Thanks for watching. Goodbye.